Welcome back to Math 151. In the last two videos, we developed a method for using logarithmic differentiation, and we computed the two examples that are on your screen. Both of these we did with a three-step method, but at the end of the last video, I promised to talk about the mysterious 0th step, which is to decide when do you actually want to use logarithmic differentiation. When is this helpful or faster than what you already know? The key to understanding step 0 is actually in step 1, which was to compute ln of f of x, where f is the function you want to differentiate, and simplify with log rules. If we understand log rules well, then we can see ahead of time, is this going to be useful or not? So, what are the log rules? Here they are. These are the three log rules written just for natural log. They're also true in other bases, but we don't need that right now. How do you actually apply these? Well, in the last video, our function, the thing we wanted to take the natural log of, was this big mess, sine of x raised to the 7th times e to the x divided by x squared plus 1. So, how am I going to do this? Well, the first thing I'm going to do is use this rule for quotients and say this is a quotient, so I'm going to have ln of the thing on top minus ln of the thing on the bottom. And now, this term, ln of the thing on the bottom, is as simple as it gets. You cannot simplify across that plus sign. There's no log rule where there's a plus inside. So that term is done. The other term, however, is a product. We have a rule for products, so we can use that and get ln of the first thing, which is sine x raised to the 7th, plus ln of e to the x, and then minus that term that we're done with. We just have to carry it along with us, not changing it anymore. And now it's time to use the last rule, which is about powers. Both of these two terms, first two terms, have a power. So you can bring it down outside. This 7 comes outside to get 7 ln sine x. And this second term here, ln e to the x, that x comes down, and then you have ln of e, which is 1. Or you could just remember right away that ln and e to the x are inverse functions, so they give you the identity function x when you compose them. Either way, this second term simplifies to x, and that third term is just coming along for the ride. That was the expression that we got in step 1 of the last video. And the reason that this was so useful is because now in step 2, when we differentiate, each term is not that hard to differentiate. It's just the natural log of some simple function, or even simpler than that. So that's the goal. We want this thing, this f that we start with, to be compatible with these rules. So we want products, quotients, and powers, but we don't want things like sums and differences. Well, you might be saying, hey, wait a minute, this function has a sum in it, right there. Yes, you're absolutely right. And that sum stayed with us at the end. At the very end of all our simplifications, we still had that plus sign there. The key is that the plus sign is not occurring sort of at the top level. If you think about how you would actually compute f of x here, you would assemble three pieces. You would assemble sine x to the 7th, figure out what that is for your x, and you would figure out what e to the x is, and you'd figure out what x squared plus 1 is, and then you would combine these three with products and quotients. The plus is happening at a much lower level. So, those pieces that we assembled with product and with quotient are the things that we ended up with here at this second stage. And then we were able to simplify a little bit further in this case because two of those pieces had powers. So the fact that that plus happened very early on in our computation meant that here, where that plus ended up inside the natural log, it wasn't too complicated, so it was okay. So let's have a non-example. Here I've written fx is x to the fifth plus 5 to the x. What happens if we try to use logarithmic differentiation here? In step 1, where we compute the natural log of f of x, we have a natural log of a sum. The two basic pieces here are x to the 5 and 5 to the x, and they're combined with a plus. We don't have any log rule which tells us what to do with this plus sign, so we are stuck. We can't do any simplifications in step 1. So we just have the natural log of fx. Moving on to step 2, when we differentiate, we get f prime of x divided by f of x as always. And now what happens when we differentiate the right-hand side? Well, we're differentiating log of something, so whatever's inside goes in the denominator. And then whatever's inside, we also have to take the derivative and multiply by. Well, wait a minute. That thing in the numerator, that's what we wanted all along. Right now, the goal is to figure out what the derivative of that is. And so far, we haven't gotten any help. But let's just soldier on and go to step 3, where we multiply by fx. So, as always, I just copy exactly what I have on step 2, and then I have to multiply by fx, by x to the 5 plus 5x. Now look at what happens here. We have the exact same thing in the denominator and over here, so they cancel, and we're just left with this, the derivative of x to the 5 plus 5 to the x. That's a pretty silly statement. Look what we've written here. If f is x to the 5 plus 5 to the x, then f prime is the derivative of x to the 5 plus 5 to the x. Duh! This was not very helpful. If you wanted to actually compute the derivative of f of x, in this case, what you should do is take the derivative of each term. We know what the derivative of x to the 5 is, and earlier in 3.9 we learned what the derivative of 5 to the x is. Now if you didn't happen to remember how to take the derivative of x to the 5 or of 5 to the x, then you could think about using logarithmic differentiation on a single term. On a single term, not on many terms added together or subtracted. When you're adding or subtracting together at the top, you're always going to have this problem in step 1 of getting stuck, because there's no log rule that will break up the sum or the minus. So here are 4 derivative questions. What is the derivative of tangent x, all raised to the x minus 7? What's the derivative of x minus 7 times tangent x? What's the derivative of x minus 7 times tangent x? And what's the derivative of the quotient tangent x divided by x minus 7? And my question to you is, which of these are good candidates for logarithmic differentiation? Before you go on to the next video, decide for yourself which of these would you try to use logarithmic differentiation on. And for the ones that you think you should use logarithmic differentiation, try to do it. The next video, we're going to solve all 4 of these problems.